Hello students. As we know that in the case of chemical reactions of Halo Arenes that we have to discuss in our last sessions, both Halo Alkanes and Halo Arenes, at that time we have to consider a new species is also vinyl halide. But we know that Halo Arenes and vinyl halides are extremely less reactive than Halo Alkanes towards the nucleophilic substitutions reactions. What are the reasons behind that? That because why the low reactivity of aryl and vinyl halides, that we have to discuss with some first point is resonance effect, then difference in the hybridizations of carbon atom in CX bond. Next point is the polarity of the carbon halogen bond, then instability of the phenyl cation and electronic repulsion. So these factors which affects to the haloarene compound for the nucleophilic substitutions reactions. So today we start the replacement of a hydroxyl group in the case of haloarenes. So we know that due to low activity or reactivity, this nucleophilic substitutions reactions in any aryl halide, either chlorobenzene or bromobenzene or iodobenzene, whatever, right, they occur under a drastic conditions. Here the drastic conditions means high temperature, high pressure is required. For example, if I give the example of chlorobenzene, when is heated with a aqueous NaOH solution, sodium hydroxide solution, at 360 degrees centigrade temperature and 300 atmospheric pressure. So which gives firstly a compound is sodium phenoxide. First they form a phenol, but as we know that phenol is acidic in nature, so it reacts with a NaOH, so it's a one type of titration reaction and we get a sodium phenoxide as a reaction. Now this sodium phenoxide, which upon acidification, because we know that this sodium phenoxide is basic in nature, so we have to neutralize with dilute hydrochloric acid, so there is a acid base reactions and we get the product of phenol. This reaction is called as a down process. So this is down process is nothing but it's a one type of manufacture of phenol. Okay, but you observe that there is a drastic conditions that we have to use. First, the concentration is too high, 6 to 8%, right? Number two, 360 degrees centigrade temperature and 300 atmospheric pressure. So it's a very good drastic conditions that is required. So what can do? So these reactions is fruitful for us. So at that time, we know that displacement of halogen in haloarene take place under drastic conditions. But however, it can observe or it has been observed that the presence of electron withdrawing group. If we introduce an electron withdrawing group in chlorobenzene, for example, if I introduce a nitro in chlorobenzene or cyanide group, whatever, electron withdrawing group that we have to discuss in our hydrocarbon lesson when we have to discuss about the meta-directing group. So any type of meta-directing group, and particularly in our textbook they suggest a nitro, another cyano, whatever the group, right, they are electron withdrawing group, but mind well at ortho and para position, not at meta positions. They located at ortho and para position, not at meta position. So because at that time the halogen greatly activates the halogen towards the nucleophilic displacement reactions. If greater the number of such a groups at ortho and para positions, it means that your halogen is more reactive in the haloarene. For example, if I take an example is like that. As we know that in this case only chlorobenzene, no electron withdrawing group that we have to observe in this case. So we get a drastic conditions is required. But now compare this example if I introduce nitro group, right, at para position or ortho position, right, but not at meta position. Why not meta position? That we have to discuss in the case of mechanism and the explanations of this mechanism. So when we have to perform this 1-chloro-4-nitrobenzene, look, here 15% of NaOH is used, but the temperature is too low, 170 degrees centigrade only, while in this case 360. and no pressure is required. It's a great news. No pressure is required, because as we know that pressure in the industries to particularly put the pressure in the reactions is most expensive process. So here no pressure is required, and then we have to acidify it with the dilute HCl. So we get a product is para-nitrophenol. This is called as a para-nitrophenol, because there is a what the mechanism that we have to understand in our later portion. Okay, now I introduce one more electron withdrawing group at ortho position, one at para position, one at ortho position. So it's called as an 2,4-dinitrochlorobenzene. But mind well, so when we have to use a 15%, here only aqueous NaOH is required, no concentrated NaOH is required. Temperature is too low, 95 degrees centigrade temperature. At that time your chlorine is displaced by the OH group, because this NO2 and NO2, they withdraw the pi electron clouds towards them and they stabilize the carbanion that we have to discuss in our mechanism portion. So 2,4-dinitrophenol. Next one is a 2,4,6-trinitrochlorobenzene. So 3 nitro group. If the number of nitro group, right, or greater than number of this nitro group at ortho and para positions, the halogen is more reactive in haloarene. So only water, in not aqueous NaOH, because we know the self ionization of water is also produce OH minus, and it's too low temperature. Is normal is almost warm water, 50 degrees centigrade temperature is required. At that time chlorine is displaced with OH and we get the product is 2,4,6-trinitrophenol, or sometimes it's called as an picric acid too. Other name is picric acid. Okay, this is such a type of acid who does not having a COOH group, but even though it's because it's acidic in nature, because they're having an electron withdrawing group. So chlorine which can be displaced with the help of OH, right, with these reactions. So this compound is picryl chloride, sometimes called as picryl chloride too. It's converted into picric acid. So what is the point? Why this electron withdrawing group at ortho and para positions activates the halogen towards the nucleophilic displacement reactions? That we have to understand with the help of such a type of mechanism, because in your textbook, right, they give such a type of data. Okay, fine. First you have to observe ortho. This is para position, because attack at para position. So if we use a nitro group at para position, so we know that there is it's a OH minus. This compound is OH minus. So it's a nucleophilic attack towards the chlorine, right? So first step is a very slow step. So these are the resonating structure. These are the resonating structure that we have to observe, because this is a canonical structure too. So what we have to observe in this case, when OH is attacked at this chlorine position, so definitely the position at that time your pi cloud is delocalized on ortho position, then number 2 position, then number 3 positions. It's a one type of hybrid structure, and then fast step. So at that time chlorine is removed. So this type of the structure. So what we have to understand in these reactions, so the presence of nitro group, here the presence of nitro group at para position, right? This is another attack at ortho position. Same way, if OH minus is attack on chlorine, slow step. So at that time we get a different resonating structure, then hybrid structure, and last one is the fast step. This is the fast step, and we get a product is like that. We get the product is like that. Okay, this is little bit light due to the 4-color printing. So what we have to observe first, when the presence of nitro group at para position and ortho positions withdraws electron from the benzene ring, they withdraw the electron, and thus they facilitates the attack of nucleophile on halo arenes. Here in this case we observe a carbanion is formed. Where you have to observe the carbanion, this is carbanion. Same way here carbanion, right? This is the main point. The carbanion form which is stabilized by the resonance. This carbanion is stabilized by resonating structure. But you have to firstly observe, in case of this ortho and para dinitrochlorobenzene, the one of the resonating structure, out of this resonating structure, one of the resonating structure, for example, in this case, this 2, first you have to focus on 2 number structure. What you have to observe in structure number 2, so here in this case, your carbanion is a negative charge on the carb atom, they having a nitro group. Therefore, this carbanion minus, because it's an electron withdrawing group, so this carbanion is highly stabilized with this group. So this structure or out of these 3 canonical structure which stabilize the hybrid structure. Okay. Therefore, this carbanion is stabilized by NO2 group as well as the pi electrons of the benzene ring. So in the case of ortho, okay, fine. So in the case of ortho, you observed which structure at ortho, it's a carbanion. So this is carbanion, the structure number 4. You have to observe structure number 4, where your carbanion is stabilized by electron withdrawing group. So they decrease the amount of negative charge. So they stabilize the pi electron cloud in the resonating structure. But however, in case of meta, this is the case of meta. You observed in the case of meta, right? In the case of meta chloronitrobenzene, here the carb anion is not stabilized by nitro group, because here carbanion next and next. So we know that the resonance of carbanion at ortho and para positions in benzene ring or phenyl ring, but here our nitro group is attached with the meta positions. So nitro group is not stabilized by this carbanion, or other means this carbanion is not stabilized by nitro group. So the carbanion resulting in ortho, so it means that carbanion resulting in ortho chloronitrobenzene and parachloronitrobenzene are more stable than the resulting form of metachloronitrobenzene. So thus the presence of electron withdrawing group at ortho and para positions, right? Halogen activates the aryl halides towards the nucleophilic substitutions reactions. Further, as the number of nitro groups are increasing, if I use one more nitro group, so it means that the resonating structure, so at the time two different canonical structure having a carbanion joined with a nitro group, so they increase the stability. So due to more resonating structure, so it may be noted that although the presence of nitro group at meta position, this is the presence of nitro group at meta position, the halogen does not stabilize the resulting carbanion by resonance effect. So halogen which cannot be stabilized by this resonance effect. So it means that it does stabilize it somewhat by inductive effect as compared to the carbanion. So consequently, we say is that metachloronitrobenzene is more reactive than chlorobenzenes towards the nucleophilic substitutions reactions, right? So, in the case that we have to observe with the help of this different mechanism that we have to discuss, right? Now, the next point. So, after the nucleophilic substitutions reactions, now we focus on to the another portion is number 2. And this number 2 portion is called as an electrophilic substitution reaction. Electrophilic substitution reactions. So most of the time in the case of arene compound, at that time when we have to discuss about the aromatic ring with a certain functional group, at that time we have to definitely focus on this type of the electrophilic substitutions reactions. As we know that under the title of electrophilic substitutions reactions, we observed a nitration, sulfonation, chlorination, bromination, Friedel-Crafts alkylation and Friedel-Crafts acylation. Why these electrophilic substitutions reactions in the case of halo arene? So halo arene undergoes the usual electrophilic substitutions reactions of the benzene ring such as halogenation, nitration, sulfonation and Friedel-Crafts reactions. Halogen atom is slightly deactivating because chlorine is more electronegative. For example, if I take one more example, first I start with a halogenation. nature. We know that chlorobenzene, in the case of chlorobenzene, chlorine is highly electronegative than carbon. So the electron partially direct towards to the chlorine. So chlorine having a delta minus and carbon having a delta plus. This is the reason that chlorine is little bit due to inductive effect is slightly deactivating group. But we know that the lone pair of the chlorine, which they donate towards to the phenyl ring and they converted into resonance effect. So it's a ortho para directing group because they donate the electrons to the ortho and para positions. So ortho-para directing influence of this halogen atom can be easily understood if we consider the resonating structure of chlorobenzene, which can be given in our last session. Okay. So in other words, because of this resonance, the electron density increase more at ortho and para position. So it means that further electrophilic substitution reaction in halo arene mostly occurs at ortho and para positions. However, because of such a steric hindrance at the ortho position, the para product is usually predominates over the ortho products. Because number two, the halogen atom, because of its minus inductive effect, has some tendency to withdraw the electron from the benzene ring. So as a result, the ring gets somewhat deactivated as compared to the benzene. Hence, further electrophilic substitution reactions in halo arenes occurs slowly, so under more drastic conditions are compared to those of benzene. Now, step by step, if we consider the reactions, for example, chlorine in presence of anhydrous FeCl3. So we get a product because it's an ortho-para directing group. So Cl and Cl at ortho position, same way Cl and Cl at para position. Right? So ortho-dichlorobenzene and para-dichlorobenzene, but this product is major in nature. This is because due to steric hindrance, always para is predominant over ortho. Number two reaction is called as a nitration reaction. So what we have to observe in nitration reaction, when we have to perform the chlorobenzene, right, when it reacts with a concentrated HNO3, because in the case of nitration we have to take a concentrated HNO3 and concentrated H2SO4. Firstly they combined with each other and they form a NO2 plus, and this NO2 plus electrophile, which can be attracted with the help of pi electron cloud of this phenyl ring at ortho and para position. So in this case we definitely observe two different products. One is 1-chloro 2-nitrobenzene, and number 2 1-chloro 4-nitrobenzene. 1-chloro, but this product is major in nature and this is minor in nature. Why this is major in nature and minor? Because ortho having a steric hindrance problem, so para is predominantly over ortho. So two reactions, halogenation and nitration. Then okay, number 3 reactions. Then number 3 reactions. So this number 3 reactions is called as a sulfonation. It's a sulfonation. So what is in the sulfonation process? In the sulfonation process, you have to take a chlorobenzene with the help of concentrated H2SO4, or sometimes we have to take a oleum 2, H2S2O7, right? It's a fuming H2SO4, sometimes it's called as a fuming H2SO4. So now chlorine and SO3H group, SO3 first H2SO4 and SO3 is formed as a fuming H2SO4, and this SO3H plus is attracted towards to the pi electron cloud, and we get two different products. So first product is called as a 2-chloro-benzene sulfonic acid. 2-chloro-benzene sulfonic acid. This is 4-chloro-benzene sulfonic acid. This one is major in nature and this one is minor in nature. Then number 4. Number 4 is called as a Friedel-Crafts reaction. It's called as a Friedel-Crafts reaction because invented by Friedel and Crafts. So what we have to do in these reactions when chlorobenzene is reacts with methyl chloride in presence of anhydrous AlCl3, right? So this is called as Friedel-Crafts alkylation. This particular process is gone through first anhydrous AlCl3 reacts with Cl3Cl, so they form a Cl3 plus carbocation, and this carbocation is attracted toward to the pi electron cloud of chlorobenzene at ortho and para position. So compared to the ortho, para is dominant in nature. So we get a product is like that, ortho and para. Ortho and para. The name of this compound is 1-chloro-2-methyl benzene. Here 1-chloro-4-methyl benzene. Sometimes it's called as an orthochlorotoluene and parachlorotoluene 2, major and minor. Next one is a Friedel-Crafts acylation. Next one is Friedel-Crafts acylation. So in the case of Friedel-Crafts acylation, same reaction, but we have to take a first chlorobenzene, but here CH3COCl. This is called as an acetyl chloride or ethanoyl chloride 2, right? It reacts with a anhydrous, because this anhydrous AlCl3 is act as a Lewis acid, reacts with Ca3CO, so it's converted into Ca3CO plus and Cl minus. And this Ca3CO plus is electrophile, which can be attracted towards the pi electron cloud of chlorobenzene. So we get a product is like that. So we get a certain type of product. This is Cl, CO, CH3, and same way Cl, CO, CH3. One at ortho position and remaining at para position. What is the name of this compound? This is 2-chloro. Acetophenone. Right, and this is 4-chloro acetophenone. This product is major in nature and this one is minor in nature. So this is all about the Friedel-Crafts reactions. Under the title of Friedel-Crafts reactions, first is alkylation and remaining is acylation. So these are the reactions of electrophilic substitutions reactions. Under the title, we have to go through such a type of reactions. Then next point is reactions with metals. So third reactions is reaction with metals. What we have to do in the case of this reaction with metals? So in the case of reactions with metals, so we have a various type of reactions. So out of them, first we have a Woods-Fittig reaction. We know that the Woods reaction is used for alkyl or haloalkane, but here Woods and Fittig. So if one compound is alkyl and remaining is haloarene, so this combination is called as Woods-Fittig reactions. Concept in both the cases same. First we have to take a, for example, if I have to take a bromobenzene. When this bromobenzene reacts with granules of sodium in presence of ethyl bromide, so one species is haloarene and remaining is haloalkane. If we perform these reactions in presence of dry ether, same way we get a product is like that. Okay, CH2 CH3 plus twice NaBr is released. So this compound is called as an ethyl benzene. So this reaction is called as an Woods-Fittig reactions. So what about the Fittig reactions? So in the case of Fittig reaction, so what is in Fittig? In Fittig reactions, you have to take a 2 moles of Halo Arenes. Okay. So when they react with in presence of dry ether, so we get a product is like that. It's diphenyl plus 2 NaCl. So this is called as an diphenyl. Right? When only haloarenes are treated with sodium, this reaction is called as a Fittig reaction. But when treated with a haloarene as well as haloalkane or alkyl halide, so we get a product is called as a Woods-Fittig reaction. So in our textbook, they discuss about these two reactions, Woods-Fittig reaction and Fittig reaction. There are another Ullmann biaryl synthesis, but that cannot be discussed or with the help of Grignard reactions with lithium. So this type of reactions which cannot be explained in our NCERT textbook. So at presently we are focusing on mostly on this type of the NCERT textbook reaction. So today I think so most of the compound or chemical properties of haloalkane and haloarene is over. In next lecture is a little bit descriptive lecture, because now we move to the polyhalogen compounds. So in the lecture of we have a certain types of dichloromethane, trichloromethane, triiodomethane, tetrachloromethane. Okay, so it's a one type of descriptive topic, but we have to take such a type of lecture that we have to know what is the uses of how to manufacture and what are the disadvantage of this compound. Okay, thank you very much.